A regression model builds on a correlation. So if you know the concepts of a correlation, the regression model will be easier to digest. So this video assumes that you already know what a correlation is, and in particular, I mean a Pearson correlation, okay? And the very simplest regression model is between two scale variables. And the regression model also talks about the relationship between those two scale variables. But what's a little bit different is that we have a bonus of prediction, meaning that we can predict y with x, or we can predict our outcome variable with our predictor variable, or you can say we can predict our dependent variable with our independent variable, depending on what type of design we have. So you can have experimental or non-experimental. Anyways, we predict this with a line, and we can give our line a equation here. So if you remember back in linear algebra, hopefully this looks a little bit familiar, you have y equals mx plus b. So you have this equation here, and this was from linear algebra. So we're going to use this concept from linear algebra and apply it to sample data. Okay? And we're going to use slightly different notation. We're going to use y equals bx plus a. But it's the same sort of concept, okay? And I'll show you that in a couple of slides. Okay, I'm going to review linear algebra for you. And you're probably used to using the equation y equals mx plus b. But in statistics, we use this other equation, y equals bx plus a, and that's just because we tend to use different letters. So don't let the different letters confuse you. So we're going to use b for the slope and a for the y-intercept. And the slope is rise over run, and the y-intercept is where x is 0. It's the y value for when x is 0. So let's first find the y-intercept, and from this equation that's already calculated for us, we can see the y-intercept is 4. And so that means a equals 4. Remember, a is for the y-intercept. Okay? And I'm going to make a dot here where x is 0 on the line. So I found where x equals 0. So this is x on this axis, and y is on this axis. So when x is 0, then y equals 4. Okay, and so if you want to write this in coordinates, it would be 0, 4. So that's how I know a equals 4. This is our y-intercept, right? So that's not too hard. Now I'm going to clear this, and now I'm going to talk about the slope. So the slope is 0.5, and it's right here, it's 0.5, and we're going to use it b for that. So b equals 0.5. Now I'm going to show you how we found that. And you're going to find it totally different when we go and use it with sample data, but just to give you an idea of what it really means, we'll find it how you did in linear algebra. So just going to find two dots here. one here. I'm going to use this one. So I'm just picking two places on this line, but I'm picking these because it's easier to find the coordinates because they are on a whole number. So this is, for example, this is 0, 4. And this one is 4, 6. Okay. So I'm going to use these two dots. And I'm going to find the rise between these two dots. So if we make a dotted line here, this from here to here, so the difference between their heights is 2. See that? 6. So we can do 6 minus 4 is 2. Okay? But then we also want to know the run. So the distance between 0 and 4 is 4, right? So the distance between here and here is 4. Or you can say 4, or sorry, yeah, you can say 4 minus 0 is 4. So 2 divided by 4 is 0.5. So that's how we get this slope if you're doing it the linear algebra way. And again, I'll show you how to do it when we actually have sample data. But this is just kind of an overview of linear algebra. So now we have sample data, and this happens to be the same exact line. But now we don't have data that falls exactly on this line. It doesn't fall in a straight line, so we have to make a line that best fits the data. And so we make what's called a line of best fit. And what we do in regression is make an equation for that line of best fit. And what the technology does, like Excel or whatever you're using, or you calculate it by hand, what you try to do is make a line where the distance between the data and the line is minimal. So let me give you an example. So here is our dot. So our dot when x equals 4 is right here. And where x equals 4 on the line is here. Okay? So it's a little above. It doesn't exactly predict it just quite right, but it's pretty close. So the distance between the line and the data here is what's called a residual. And each of these have a residual. This dot is actually on the line, so its residual is 0. But you can also do it for this dot. So here's another residual, is the distance between the line and the dot. And I mean vertically. And then here. So we have one for each dot. So what you try to do when you make a line of best fit, you reduce the total amount of residuals which is the distance between the line and the data. and that is vertical distance. Okay, so this is what you try to do when you create a line of best fit, and I'll show you how to do that. And to get this line, you need two things, two pieces of information. You need the intercept and the slope. So instead of having one average for each group like you do in a ANOVA or a t-test, we now have a predicted value for each value of x, and that's the dot that's on the line. So here, and here, and here, these are the predicted value for each value of x instead of having an average for each group, because we don't have groups anymore. We have two scale variables instead of a categorical variable and a scale variable. And the line of best fit, the line of predicted values, we try to reduce the total distance between the actual y's and the predicted value. So the actual y's is the dots, and the predicted value is where the y is on the line. And so the line of best fit tries to reduce the total distance. Okay, and then here you should also note that if we put a line at the average of the predictor and the average of the outcome, so we can see that the average of the predictor is 4.67 and the average of the outcome is 6.3. And so you put a line at both of those, and where that intersects, it will always be on the line of best fit. And that's just good to know for later on when we're calculating the intercept. You need to know that. Just keep that in mind. Now I'm going to kind of compare and contrast the intercept and slope. So say we have this coordinates, and so I'm going to draw three lines that have the same slope. But different intercepts. Okay, so here's one line, here's another one, and here's another one. So they kind of increase in the same amount. It's not perfect because that's drawn by hand. But you can see the intercepts where they hit the y-intercept here when x equals 0 is different. Okay? Now I'm going to draw where we have the same intercept. But different slopes. Okay, so let's see. Here's a positive steep slope. Here's a slope of 0. There's really no relationship. And then here's a negative slope. And they all about hit the y-intercept about the same place, which is right here. So we have the same intercept, but different slopes. Again, we have a positive slope, no slope, and negative slope. So this one's positive, this is 0, and then this one's negative. So when we interpret the intercept, we say something to the effect as when x equals 0, y is predicted to be whatever the slope number is. And when we interpret a slope, we say for each additional unit of x, y will increase by whatever. So I'll go more into detail about that later, but this is kind of the generic interpretation, so you should probably write these down. So earlier on in the video, I said that regression builds on correlation but has added bonus of prediction. So we can predict what y will be for a certain value of x. So for example, here's our equation: y equals 0.5 x plus 4, so our intercept is 4 and our slope is 0.5. And we want to know what we predict y to be when x equals 5. So if x equals 5, what is the predicted value of y? And we can put this in the equation. So we're just going to fill in the equation. So y equals 0.5. And we're just going to fill in x. And we want to know if for x equals 5 plus 4. So y equals 2.5 plus 4. So y equals 6.5. So if we go back to the graph here, so when x equals 5, which is where this line is, by drawing, we go and make a dot here on the line, and then see where that is. For the y value, it's about, it's hard to see on this little graph, but that is 6.5. So this dot here is at 5 and 6.5, if you put that in coordinates. Okay, so that's just what it means about the predicted value. So it's where the y value were on the line for the x value. So let's do another one. So say you want to know when x equals 10. So we just put y equals 0.5 times 10, just filling in that x value, plus 4. So y equals 5 plus 4. So y equals 9. So again, if we go make a line here where x equals 10, and then we see where that is for the y value, it's about 9. So this dot here on the line where x equals 10 is 10, 9. Alright? When we're doing regression, we have two parameters that we estimate. We estimate the slope and we estimate the intercept. So we can have two different significant tests for regression. We can have one for the slope and one for the intercept. Generally, we use a t. We can also use a f. But generally, we use a t statistic. And generally, they're two-tailed. And there's not really a good reason why they're usually two-tailed. I think it's just the default of statistical software that it's two-tailed. So whether you're using Excel or SAS or SPSS or R, whatever software you're using to do the regression, generally the default is a two-tailed test. So people just generally do what the software does. So just note that. And we generally want to see if the slope is significantly different from 0 and if the intercept is significantly different from 0, and these are also defaults. These are what we're going to do in the class. We're going to see if the slope is significantly different from 0 and if the intercept is significantly different from 0. But you don't have to do this, but this is what people do 99% of the time. And so if the slope is significantly different from 0, it just means that there is a relationship between the two variables, just like in correlations. Okay? And if the intercept is significantly different from 0, sometimes that's meaningful and sometimes it's not. Sometimes 0 doesn't really help you very much to know that when x equals 0, y is different than 0. Sometimes it is, but most of the time it's not very helpful. And most of the time we just use the intercept for prediction purposes, and we don't really care if it's significant. But we're usually interested in knowing if the slope is significant because we want to know if there's a relationship between the two variables.